How's your conference been? It's great to all be together doing this face-to-face, right? Instead of talking to a webcam for an hour and then disconnecting and returning to work. So, my name is Hannes, I'm from Belgium, and today I want to talk to you about doing DDD and CQRS-based systems using aka.net. So what's on the, see, clicker doesn't work? Yeah, it's there. So what's on the agenda for today? I'm first going to describe a little bit what we're building, because you always want to have a problem domain when you're giving a talk. Then I'm going to discuss the general design ideas that I want to achieve. I'm going to explain why I would want to use aka.net to do this, and then I'm going to dive into bits and pieces of the codes and features of aka.net which make it very suitable to do this. And then, if I have time, we're going to wrap things up. So, what are we building? We're building beersender.net. Why are we building beersender.net? I had a particular set of problems. It was January 2022, and the whole world was on lockdown, and I was very bored, and I wanted to do something. And then I had an idea. I live in Belgium, so we have great beers. How about I put some of those beers in a box and I ship them to some of my friends so that everybody will be happy. So that was my plan. So I went to the store, and this was the fun part. I mean, we have lots of local beers in Belgium. So I selected the best beers from my region. I mixed them with some of the Belgian all-time classics. So I had a very nice selection of 24 beers. I put them in really nice boxes that allowed me to ship them safely. I packaged them up, I put shipping labels on it, and I thought, this was fun, my job is done, right? And the expectation of my story was that all the boxes would leave in Belgium, and this would happen, right? Well, no. Because the reality was that I gave these boxes to UPS, but some of the boxes would be leaving the European Union. And I didn't really expect what was going to happen. So what happened was, nah, sir, you don't have a license to send beer. We're going to return these boxes to you. So what happened was that I had to track all these packages, see where they were coming back to me. I had to provide extra info to customs. That info wasn't accepted, so I was emailing back and forth. Dealing with the UPS help desk is like a whole different kind of hell. Then the packages were returned to me. I had to recuperate the shipping costs, send them again. Then there was one package in the UK that was not delivered, and they didn't even make a delivery attempt, but they returned it to me anyway, so I had to recuperate that money again and then send it out again. And they're almost all at their locations. We're end of April. So yeah, this was no fun. So sending beer is tricky. Like making and filling the boxes is really fun. But all of the rest of it is not so much. So we need a beer tracking system, right? That's what we're building. We need an app for that. So we're building beersender.net. And why do we call it .net? It is not built in VB6. We're using the .net framework. So yeah, why do we still do that? Like append .net to application names. I mean, it's been more than 2 decades. So yeah, that was the preamble. Now, when I'm building software, I've been doing this for a while, and I always wonder, what kind of architecture do we want? What do we want to achieve? And this is one of the inspiring books that I've read throughout my career. For those of you who are not familiar, I'll try to summarize it in 4 sentences. I'm probably not going to do it justice, but the whole idea of DDD is that you'll really try to align the language that is being used in the business and the language that is being used by your team and in your code, and you try to align that as much as possible and try to use one language, a ubiquitous language in your business. And on a high level, like a full enterprise systems level approach, you're gonna look where the bounded context, the boundaries in your systems, your services, if you will, where they can be. It's like where one language starts existing and the other one stops. For instance, in my shipment, When I'm filling a box with beer, the contents of the box are important. I don't really have to know who I'm sending it to yet, but when the same box is being shipped, there's different properties where we mean different things by different statuses. So you try to compartmentalize that into different contexts. But on a low level, we try to make our code as expressive as possible, and we have different techniques for doing that. And one of the roots for reasoning about your code in DDD is called the aggregate. So like an aggregate is a thing that you're thinking about and where events come from and where you're doing different manipulations, and it's basically a unit of reasoning for that code. And when you translate all of this into code, you can do it in many different ways. I mean, the original books were written very much from an object-oriented approach, but in the DDD world, people have moved to message-based systems using commands and events and CQRS and event sourcing and all that sort of stuff. So when we're talking about commands and events, because this is something that we will see in my beerstender.net application, when we're talking about commands today, we are telling the system to do something. It's a request to perform a certain action. And that request, we are always going to put it in the imperative form, send the beer, send the box, update the tracking number. An event is the opposite. The event is what comes after it. After the action has succeeded or failed, events will be raised. So the events are in the past tense. The beer has been received, my ultimate goal. My friend has the beer and they're happy. And they owe me beer, which is the best part. It communicates that the action has taken place, right? So once you have that, it's like, how am I going to put this into an architecture that scales well? And one of the concepts that it's not necessarily necessary to do this for a DDD system, but CQRS is used quite a bit. And the reasoning about CQRS is you're going to separate your command side and your read side from your system. So when you're sending commands into the system, they will actually mutate the data. But when you query the system, you're actually not changing anything. And by separating the two sides, you'll be able to scale them independently, use maybe different technology stacks on both sides, and get something that can really handle lots of requests. But for this to succeed, you have to be able to send the command into the system and make sure that it never fails. It always has to succeed. And it can change state and it can raise events. And the events that are triggered there, and they're actually sent over whatever technology you choose to the read side of things. And on the read side, these events are projected and they will update your read storage. And you can make that very, very performant. You can just use a relational database, but make sure that every query hits a single table on an index, so it will be snap fast every time. That's like some of the things that you can optimize for. Now that's CQRS. And then the last concept that I just mentioned is event sourcing. And again, you don't have to use it, but it's really nice if you do. Because when you save state in like a classical object-oriented system with a relational database, you're saving the data as is. Like a normalized database has a state of your system at the current moment. But you're losing data. Like a classical example is a shopping cart. Customer puts in product A, keeps browsing the site, looks at the suggestions, sees product B, is like, oh, that's better, I'm going to put B in and remove A. Your shopping cart contains B, but the valuable info for your recommendation engine, for instance, is that they first put in A and then removed it again, right? And that's what event sourcing is all about. We're not just going to store the resulting state. We could store all the events and then project the state from that. And that is what event sourcing is. So if we put all that together, what I want from my architecture is I would want to do CQRS with event sourcing. And I want to have really clean aggregates, so code that is easy to use, easy to read, that everybody can take a look at. And if at all possible, I would want tests that my product owner can understand. Because if we're going to use the same language between the business and the programmers, it would be so cool if we could write our tests together so that they understand what the software is supposed to do. And you can prove to them afterwards, like, I built what you ask. Anybody ever had that discussion before? Yeah. So you know why you want to prove that you built what they ask, right? So when I was shopping around for technologies, I wasn't really shopping around because I've been working with Akka.NET for a long time. But Akka.NET, for those of you who don't know, is a port of Akka on the JVM. Akka is a product built by Lightbend, often used together with Scala. And in 2014, 2 people independently from each other started porting it to the .NET ecosystem. And then they joined efforts, and in April 2015, we have gotten the first release version of Akka.NET. They actually called it that with permission from Lightbend, so nothing new there. But what we're doing with one of these actor models is we're gonna model software after the way the world works, with objects that interact with each other. There are messages being sent back and forth, and you don't always know the result of what's going to come. It's not all going to be synchronous. So it's message-driven, they're using reactive patterns, and it is very, very highly concurrent. You can really make use of multi-core processors, you can make use of clusters, and you can basically maximize your performance out of that. It scales pretty linearly. It also has a lot of resiliency built into it. But to me, the fact that appealed most when I was talking about this DDD CQRS system is that we're going to model software after the real world. And in DDD, we try to make our ubiquitous language between the business and the programmer the same, so it makes sense. I mean, there could be something there. So if we explore how Akka.NET works, is the basic building block of any actor system is an actor. And it's a simple object. You inherit from a certain class, and that object holds its own state and its own behaviors. And the state and the behaviors are just encapsulated. You have no way of modifying it from the outside. And the only way to talk to an actor is to send it messages. And the messages go into an inbox, and they are processed one by one in order. And that's important, because the one by one means that there's always only a single thread running on your actor. You don't have to deal with locks. You don't have to deal with race conditions. When you're executing, you're processing a message on an actor, you know that there's only going to be one thread. And that's really powerful, because multi-threading is hard. Anybody ever tried to manage their own thread pool? No, you probably committed suicide, so you're not here, right? So the guaranteed single-threaded thing is really powerful. Now, the simplest actor that we can write looks something like this. We inherit from untyped actor, and we implement the onReceive method. And the onReceive method is what is called whenever a message comes in from the inbox. The whole system around it will dispatch it on a thread on your object, and then you can check what type it is and do something with it. So it's not really that hard to understand, and everybody who has seen .NET before will actually get that. Now, the messages are even simpler. You don't have to inherit anything. You can use any plain old CLR object to use it as a message, right? Now, what you have to keep into account is you can basically violate this no race conditions thing by changing a message while it's being processed by the actor. Now, don't do that. I mean, you're not going to have fun. And you have to keep into account, if you're running in a cluster, that your message might cross machine boundaries. So it might be serialized and deserialized. Now, the throughput that the people from Akka.NET claim is that they can get 50 million messages processed a second on a single server. My laptop gets, with the previous version of Akka.NET, it got like 3.5 million messages a second because they improve performance quite a bit every release. Like 3.5 million on a 4-year-old XPS. I'm pretty sure that on a decent server, the claimed numbers will be in the right order of magnitude, right? So we've got actors, we've got messages, nothing really hard, but we need something to tie it all together. And this was the Metallica album that I grew up with. I'm that old. Now, the actor system is your puppet master. It does everything. It manages your thread pool, it manages your inboxes, it dispatches messages to the actor instances, it creates the actors, it throws them away, it manages a built-in event bus, and so on and so on. It does all the heavy lifting for us. So we have to write lots of code to have one. We do actor system.create, and we give it a name, and we have an actor system. So it's lots of work. Now, the thing that you have to remember is that the actor system is responsible for creating all your actor instances. So we will never hold a reference to the actor object. So what you do is you use something called props. And the best way to describe props is a constructor pointer. You tell the actor system how to instantiate your actors, which constructor to call, which parameters to pass. Now, this is calling the default constructor without any parameters, but it will create a myActor. And then I can do system.actorOff, which will create that actor for me. And what I'm getting back is not the actual actor, it's an iActorRef. And the iActorRef is a little object that allows me to talk to the actor. I can use a .tell, and that will actually send it a message. This will post this message into the inbox of the actor, right? And the reason why we're not getting a reference to the actor is because the actor system might actually dispose of your actor and recreate it with the same constructor and the same constructor parameters. The system remembers the props that it was created with. And in the whole memory management side of things, actors might get disposed and recreated and so on, but your actorref will actually keep working. So you talk to an actor of an actor that has been paused and is no longer in memory, the system will actually spin it back up and tell it to handle the message. So that's pretty cool. And all these actors, they live in a hierarchy. Actors can have children, and their children can have children, and so on and so on. There's 3 actors that are always there. It's the root actor, the system actor, and the user actor. And under the user actor is where you are going to create yours. All the actors that you're going to make, they live under the user actor. So the actors that you create right under that, we call those the top-level actors. And under that, yeah, your address is defined by your position in that tree. So the one on the bottom right is /user/a2/b3. Now, why is that hierarchy important? It's because parents have responsibility over children. Get to that in a second. The way you create a child, there's something nice on this slide. We also have a strongly typed actor, which will feel so much more comfortable to use if you're coming from the .NET world. That is the receive actor. So instead of having an onReceive that just takes in an object, we can register strongly typed handlers for certain types of messages that will come in on this actor. So you can call receive as many times as you want, and you can have different handlers for all the messages that are coming in. And this is how you create a child. Instead of doing system.actorOff, you do context.actorOff. In the context of the actor, that means I'm creating a child, and I give my child a name. Now, names have to be unique. So if you're creating lots of children from the same type underneath an actor, which is something you often do, you have to make sure that they all have unique names. So you're going to incorporate the ID into the name of the actor. And then what I said is actors have responsibilities over their children. I have 3 children. If I take them to the supermarket, I am ultimately responsible. If they run their shopping cart into some old lady's ankles, I'm going to be the one apologizing. If they knock something over, I'm going to be the one cleaning up. That's how it works in the real world. That's how it works with actors. If your child actors fuck up, you have to decide what to do about it. And that's how supervision works. So when an actor throws an uncaught exception, that exception is escalated to the parent. And then the parent has to decide what to do. And it can take a bunch of different actions. All of these have a different meaning. You have resume. Resume means that this error is not so bad. You can just forget about it, and just process the next message on your inbox. It's basically continue as you were, right? There is, for the more severe errors, it's like, oh, no, this is all bad. It's like, I'm going to kill off the instance of this actor because everything else is invalidated. We throw away the inbox, we throw away the actor, like, stop it all. Don't do that to your kids, okay? Don't throw away your kids. But we stop the actor. There's also an action like restart. When you tell your kid to try again, that's what you can do with your actor, except we take a little bit of an extra step. I said that actors get recreated, right? If you say restart, it actually disposes the actor instance, recreates it with the same props, and then tries to dispatch that same message again. So the inbox is preserved, but you're getting a new actor instance. And then escalate. It's like, I don't know what to do anymore. I'm going to ask my parent, and then invoke that supervisor strategy. And for reasons, you can apply this supervisor strategy to only the failing child or to all of your children. Why would you apply a supervision strategy to all of your children? It's, for instance, you've got a big workload and you cut it into small pieces and you created separate actors for all of them, which is a pattern that you often use when you're doing actor development. If you do that and the whole workload is invalidated if one of them fails, it doesn't really make sense for all of them to keep processing, so you will just like stop the whole workload and apply it to all of your children. Something you can do. Now, in code, you have to override the supervisor strategy method. And you just return the strategy that you want to use. So if you want to do the one-for-one, you will have something called a local decider, which is that function that you see there. And the local decider you're able to inspect the actual exception. You also have information about which child is failing. But that's the info that you have, and based on that, you're going to have to return what to do. So you return whether you want to stop or restart or escalate or whatever, right? So that's how you implement supervision strategy. Now, this resiliency may seem like it's trivial, but it is key to the high reliability that you can get with actor systems. Like the first actor system that was ever built was Erlang. Erlang was invented by Ericsson in the 80s. The research about actor system dates from the 70s. But Ericsson invented Erlang to build a telco system. And the way that telco systems worked in those days, you made a lot of money if you were able to make phone connections and maintain them. So reliability was everything. Downtime cost tremendous amounts of money. And they were able to use this strategy, like supervision and actors, to build a 2 million line code base and reach a 9 nines uptime. So 99 point and then another 7 nines. Now, to put that into perspective, that's 31 milliseconds of downtime a year. Who gets that uptime? Yeah, no, none of us. So supervision was really crucial there. Okay, it helps that they don't have to do redeploys. They spin it up and it kept running, right? And then another feature that really pulled me into using this for a CQRS system is akka persistence. Because until now, we've been talking about actors, and all of their state comes from the messages that we send to it and from the constructors. But we're not persisting any of it. If you want to persist the data inside actors so that the state gets recreated when you recreate the actor, which is something that you're definitely going to want to do. If you want to do that, you're going to need the persistence library, and that library is event-sourced by default. I'll show you in code in the next slides, but the life cycle of one of these persistent actors is it will query the snapshot store to see what the last snapshot was, and it will recover that on the actor. And then it will query the event store and see which events have taken place since that snapshot. It will replay all of those, and then it will start accepting messages from the inbox. So then the new stuff comes in. And that is really powerful, because if you have a system recycle, you can actually have some actors that recover their own state. Like, don't do this for all your actors, because you're gonna like throw away all of the performance that you gained from using actors and like sync it into your network and disk system. So don't overuse it, but it's really useful. If you want to do persistent actors, there's a couple of things that you are going to see in code. So first of all, if you want to have a persistent actor, you have to inherit from the right class, which means that they will need a persistence ID. And this ID has to be unique across the system, because that's the key that it's going to query the stores with. Now, one of the things that I usually do is group all my state into a state object. It makes snapshotting a lot easier, because if your snapshot just saves your state object, you can reinstate it by just replacing it, except for worrying about all the other stuff that's going on. And what we're seeing is we don't have receive anymore. We have command and we have recover. And command is what is coming from the inbox, and recover is what's coming from your event store. And you're going to want to do different things with both of them, because if you have a command coming in, you're going to want to persist that command, because you want to replay it when the actor is recreated. But when it's coming from recovery, you don't want to persist it again, because then every time your actor restarts, you're like messing up your event stream. And there's a bunch of things you can do with snapshots. I'm not going to dive into that too much, but if you save a snapshot, it's important to know that that happens out of thread. So if you're saving a snapshot, it gets queued to be saved, but your actor doesn't get feedback on it, except for if you register for the save snapshot success and save snapshot failure messages, and then you can do something with it. Now, what is important is you will now get inside your actor, if you're using a persistent actor, you will get a persist method. And the persist method takes two parameters. The first is the event that you want to persist to the event store. And the second is the function that you would want to call when successful. So I'm calling the method below it when my save to the database has been successful. And in that method, we're actually going to change our state. And that is the method that we're going to use when we get a recover. It will do the same thing to our state that we did before, except we're not persisting it again. And for snapshotting, you can take whatever strategy you want. You can do it every 100 messages, but you can also, for instance, have it timed. There's a whole message scheduling mechanism inside Akka.net where you can say, like, send me a message every X amount of hours or minutes or whatever. You get that in and you save a snapshot. So there's so many ways that you can go about snapshotting. Now, what you get back is when your snapshot is restored is you get a snapshot offer. And the snapshot offer contains your snapshot. You just cast it to the right type. You replace your state object. Voila, you're done. Not going to dive into those. So why Akka.net? It matches in so many ways. Both DDD and actors, they model the code after reality. It is message-driven. There is event-source persistence. There is an event bus that we can use to tie the two sides of our CQRS system together. And it is pretty high throughput. I haven't discussed clustering much, but you can run an Akka.net system across many different nodes and have linear scaling. So let's dive into some of the specifics. I've got about half an hour left, and I'm halfway through my slides. Great. It's the first time I give this talk, so timing is usually something that we want to watch out for. So disclaimer, none of this is production code. I mean, I hacked up the code to be in this presentation. I oversimplified a thing here and there, but I'm showing you all the concepts and the possibilities of using this technology for this system, and I don't want to distract too much from it. So don't go copy-pasting this and claim that you have a production system, because it's not that. But aggregates. Remember that I said I wanted really, really clean implementations for my aggregates. And I don't need Akka.net to do that. So I want my aggregates, basically, if possible, to have no dependencies whatsoever. And I want them to know nothing about the storage, and I want them to have a very nice testable behavior, right? That's what we wanted. You all agree? So we're going to try and get to the place where we can actually have our product owners read our tests. So if I'm going to be thinking about that CQRS system, what do I want my aggregate to be able to do? I want to be able to send a command to it and see what events I would get from doing that command. And for implementation reasons, I'm not going to have the command change the state just quite yet. I'm going to get a list of events back. And if I apply those events into the aggregate through the apply event method, those would actually change the state of the aggregate. I could have chosen to have the command already apply all of the state. For the akka persistence that I just showed you a minute ago, it comes out more beneficial like this. You'll see that later. So this is what I want my aggregates to do. I want to be able to check a command, and I want to be able to apply the events. So if I build a beer shipment aggregate, wait, this is pulling away. If I want to build a beer shipment aggregate, I'll have fields that I'm able to serialize. Because I'm going to be thinking about this aggregate as my state object. If I snapshot this, this is what goes into my database. So the fields have to be there. And they're going to be set through the events that are sent to the aggregate. Now, is that still readable? Yeah. So if we're sending a command in my implementation, I'm going to check what type. Oh, I'm going to check what type of command I'm getting, and I'm going to raise events. And raising events is really easy. It's IEnumerable, so we can just use yield return if we want to raise multiple events. That works really well. So we're actually checking the state of this command, and sending beer might succeed or it might fail. And I'm returning events as I want. And on the event side, I'm going to change the data. So I might write apply methods. It's one of the ways you can actually use polymorphic parameters on methods, so you don't need that switch case at the top. But this reads more clearly if you see what we're reasoning about. And so we're getting all the types of events in that our aggregate can deal with, and they will change the state. Like here at the bottom, the shipment ID is being set. Now, what does this give us? If I'm writing a generic test-based class around this, I can get to that unicorn of a product owner readable test that we want so much. So I'm writing a test-based class that allows me to test an aggregate. And that test-based class gives me a couple of methods. And the first one is the given. It lists all the events that have taken place before I'm actually going to try and run this one command. So what I'm going to do is when I call given in my test, and notice that it's a params array, when I call given in my test, it's going to play all these events on that aggregate class. And then after that, we have the when. And the when is the command that we're going to write a test for. And we're going to check that command on the aggregate and see what list of events we're getting back. And then we're going to check that. Now, if you use C# records, it's going to be really easy, and you can use equality. You can have deep checks if you're not using them, but basically what this method is supposed to do is like check that the content of all the events that I'm getting back is what I expect to get back after I replay that command given the conditions that we had before it. And this is like 2 screens of code, but that allows you to have tests like this. Given these 3 things have happened, when I try send beers, I'm expecting that the beer is sent. Now, if you use factories or static methods to create the events, you can even get rid of the new keywords if you want. But this is a test that your product owner, even if they don't know how to code, that they can reason about. This is a scenario that you can talk about with them. And to me, that is one of the big values of trying to establish this ubiquitous language of using those command and event-based systems is it maps really naturally to business processes. If I hadn't added a shipping label, I am not able to send the package. I have to add a shipping label first. So I can definitely write 2 tests for that and talk to my product owner, and we will agree. And we'll have a test that I can implement in the aggregate that is really the way that I want to have it. So these aggregates and the corresponding tests are really helping me, even without touching on actors, allow me to get really far in that process. But now we need to be able to run this code. I mean, we have to run like a whole bunch of these aggregates inside the system and have ways to ship those commands to them and have them behave. And when we recycle the system, we want them to be recreated. So we need an actor to host our aggregate in, right? So we're going to wrap that. And I want to have, I aim to have a generic implementation that I can use for different aggregate types. You don't have to do that. But I want to have one that calls persistence in the right way and it replays events in the right way and all that sort of things. So this is the entire aggregate actor. It's going to be, I think, in 3 slides. Now, the first thing is I need to have that unique persistence ID, right? So I'm going to use the type of the aggregate that we're using and the ID of the aggregate and use that as my persistence ID. Pretty sure that should be unique across my entire system. And see that we have those 2 different handlers, right? I told about that in the persistence part. We're going to have a recover and we're going to have a command. And the only difference between the 2 is that for the first one, we're going to also call persist. And for the recover, we're only going to apply it to the state. So what do we need to do for our aggregate to work correctly is that when we get a snapshot, we're actually replacing our internal aggregate. So that is the thing that goes into the snapshot store. You don't have to use any snapshots if you don't want to. And then you will just replay the event stream for all eternity. Kind of depends on your business domain what you want to do. But if you want to have a snapshot, that's how you get it. And when we're applying, we can just apply the event to our aggregate. Remember that interface that changes the state of our aggregate based on all of the events. Like that's why I pull the events out and replay them on the aggregate so that I can have the same behavior for my actor for the entire event stream. I did the same thing, like a snapshot every 100 messages, but as I said, you can do something else. And then the last part is we are going to be able to handle new commands. And this is where the magic happens, right? We're first going to ask the aggregate, like which events would you spawn if I were to queue this command on you right now, given the state that you're in. And then you get a list of events back. And those events I'm going to want to apply to the actor's state, but also save into my event store, because that's what's going to change the state. That's what I'm going to need to replay when the actor gets recreated. So we call the persist. We first do the check command, and we call the persist. And we apply the events through the same method that I just showed in the previous slide. We apply the persist on the aggregate for every event that comes out of this. And the line under that you can ignore for now, but you can already take note. We're also going to publish it to the internal event stream of the actor system. Now, this is all the code that you need to make one of those actors. If you now make a class that just implements the generic aggregate actor, all of your work is done. So making like a beer shipment actor that is basically like create class, public class beer shipment actor, it inherits aggregate actor of beer shipment, and you're done. And you can do this for all the different types of aggregates that you have in your system, and that is really powerful. Now, we've got an actor, and we've got an aggregate inside that actor, so we've got a little bit of the work done. But now we have to decide how we're going to manage our hierarchy. And our hierarchy is going to do a lot more, because we have that whole CQRS system, and all we have now is a command side, right? So this is what the basics of building an actor hierarchy for a CQRS system would look like. Our actors that we just described, they live here. They are the actual aggregates doing the work, handling the commands, right? All the other parts, I'm going to dive into over the next couple of slides. So the first thing is the aggregate manager. This is something you see in actor systems quite a bit. It's an actor that is responsible for creating child actors, right? Based on information that it gets, it's going to create children and manage those children. Now, it takes in the eventual code base, it takes in a connect request. It's like, I want to connect to a beer shipment actor with this ID. And if this manager doesn't have this actor yet, it will create it. Now, the fact that it gets created with an ID that exists in the system might trigger persistence, so the actor will get its snapshot, it will replay the events, and it's ready to do its work, right? And then it replies to the sender, and that is also a very, very powerful thing. When you're processing a message inside an actor, there are certain properties that are set before the actual processing takes place. One of those is the sender of the message that you're processing. It's an actor ref to the other actor that is sending you that message. So we don't have to know where a certain message comes from. We can just do sender.tell and reply. So if we get a connect request, after we have created the actor, or if we already have it, we could give that actor ref back and say, okay, you asked to connect to this aggregate, here is the actor ref, go ahead and talk to it. So that's the only responsibility for our aggregate manager, right? And that just creates an instance for every aggregate that we have. The vast majority of our actors will live there, like under our aggregate manager. That's where like the biggest count of actors will be in our system. And then we'll have a command router actor. The command router actor is responsible for taking in all the commands that come in through our REST API or whatever they might want to come from, right? You've all written software before, there is an endpoint, commands come in, and we're going to dispatch them to the command router actor. The command router actor is a top-level actor. It will get created when the actor system is created. Remember, like a bunch of slides back, we can just do that, create a top level, and talk to that actor. And that might, it's going to send connect requests when it has to talk to an aggregate that it doesn't know yet, so it will talk to the actor next to it. And it will get that actor ref back, it will cache that, so because usually when you run one of these systems, you're talking to the same aggregates over and over again. And then it will relay the commands to that specific aggregate actor. Now this command router might become a bottleneck, and that's something that we haven't talked about yet, is the way that it works, and you can already feel this, if we're only dispatching a single thread on an actor instance at the same time, the throughput that you can get on your inbox is limited by the amount of messages that you can process on a single thread on your CPU, right? So if you have a single core doing all the work for one actor, if you can not achieve the messages that you're putting into the inbox, your inbox will grow and grow and grow, and eventually that will cause problems. We're going to solve that in a minute, but it's a problem to be aware of. It's like when you're designing your system, make sure that you don't have any bottleneck actors. And this is like an actor that handles the complete command flow, and if your system is highly concurrent, that might happen. And then there's a couple of other things. There are deep projectors. It's like we have our event stream with all the messages in it, all the events that have taken place as a result of the commands that we have processed. And we are going to use those, remember our CQRS system, to update our query store, right? Our query store might live outside of our actor system, might be a MongoDB or a SQL database or even Azure Blob Storage for all I care. But you're gonna want to update that storage like whenever events happen. You're gonna want to write new records or update existing ones. So you're gonna create one projector for every type of event that you want to update your query storage, right? So what we're gonna have is we're gonna have like a projector creator that just instantiates all the types of projectors that you have. You could use reflection for that, like scan how many implementations of a projector that you have in your code base, spin those all up. That works really well. And the same thing we're gonna do with what I might call folding back the event stream. Your aggregates are going to want to respond to events that have happened in other aggregates or events that have happened outside of your actor system. For instance, in my case, if I get tracking updates from my shipping vendor from UPS, that's when I would want to queue those as events on my event stream as well, and that might actually fold back to my aggregates, and it might update my aggregate state. So you could, I chose to separate those from the projectors. So you're gonna create all of those at startup as well. They will also subscribe to the event bus. So it could come from anywhere. And same here, like for every type of event that goes in, you're gonna have an actor handling them. Now, I've talked to the event bus a few times, and it is something that works. It has a really high throughput inside an actor system, but its functionality is a little bit limited. So what you can do is you can publish any message, any object to the event stream. You can do this from an actor. Then you call context.system, which gives you the actor system, .eventbus, and event stream.publish, and then it goes on there. But if you have created the actor system in, for instance, a singleton instance in your API, so that API requests can publish messages on your event stream, you can just do system.eventstream, and you're doing the same thing. So you can do that, and you can subscribe to them. But there is no filter on properties. The only filter that you have is on the type of message. So that's something to be aware of, and that's also why in the previous slide I told you that you're gonna have one per type. You're gonna have one actor that has to deal with all of them, because you cannot subscribe to specific partitions of the stream based on the content of the messages. So it's always going to be the type of messages. So that is why we have those one projector per event type rules. But it's not hard. I mean, it's a publish subscribe system. And I promised you that I would also explain what you can do to your command router, right? The one that might have become a bottleneck. Now, the command router, Akka.NET has a system built in for actors that have to be able to process a large number of messages. And the thing is, if it has to handle more commands than it can handle on a single thread, we have a problem. But you can solve that with router actors. And router actors are basically, there's two types of router actors. You have pools and you have groups. And the only difference is that in a pool, the router will manage its own instances, and in a group, you will create them, and then the group will just do the routing for you. But the thing is that one of these router actors, they can use a routing strategy to decide to which actor which messages go. And that way, you can have a pool of actors that is going to handle all the requests that come in on that single address or that single actor ref that you have in the system. And that is very powerful, because you have a single actor ref that you're talking to, but there's actually 5 or 10 or even 100 actors behind it that are going to do the work. And there's like, I think there's 7 or 8 different routing strategies that you can do between your pool members. For the case that we have, these are the 3 that make the most sense. It's like round robin, like 1 at a time for every pool member. Or we could look at the smallest inbox if there is a big difference in the amount of time that it could take for a certain message to process. You could look at which of your pool members has the smallest inbox, and that's the one that will get the new message. Or you could do consistent hashing. And consistent hashing is you're going to implement a hashing method on your messages that is going to give you a hash, and messages with the same hash will always go to the same pool member. This might be interesting if you want to keep certain data in scope, for instance, like a link to my aggregate. If I want to shard all my aggregates across the pool members of my command router, then I could shard on the aggregate ID, implement consistent hashing for that, and then I know that all the commands for the same aggregate will go to the same pool member for my command router. Wow, does that make sense? You have a question? When the pool is resized, the pool size is actually instantiated when you start it up. So with consistent hashing, it knows which the members are in the beginning, and it's not resized during running. When you're just doing, there are pool strategies that can actually allow you to upscale and downscale the amount of pool members based on the load. But with consistent hashing, you're going to want all your members to be there. If you're running in a sharded situation, in a clustered situation, because Aggregate has the possibility to cluster multiple nodes, and you can basically implement sharding so that you let the actor system decide on which of your nodes a certain actor is being created. What you could basically do is shard your you could shard your aggregates across all of your nodes and then have a command router instance on that same node and make sure that consistent hashing hits that one and talks to the aggregates on the same node, and you're going to win a lot of performance. But that would take a bit too much code to display right now. But it's possible. I've done that. So if you want more info on that, like, come and see me after the talk. What we do basically is, instead of just creating regular props, we're going to tell the actor system that, okay, this is props for a pool, a round robin pool, which means that it's going to create its own instances. I want it to create 5, right? And then we do the same thing. We do system.actor_off. And instead of 1 command router, we're going to have 5. And the actor system is going to take care of the fact that the messages are distributed across them. You can use this same strategy if you're, because this is probably the first bottleneck that you're going to have to solve. After a while, some of your event projectors or some of the actors that are subscribing to the event stream, they might have a similar problem, because then that's the next bottleneck you're going to hit. You could use the same strategy there. So a single projector could also be a pool of projectors, right? We got 6 minutes left, and I'm at the conclusion. This is great. So there's so many things that we didn't talk about today. One of them is you could publish your event stream towards the UI, which is like a lovely thing to do if you're building a CQRS system. If you could subscribe to the event stream from the UI, you can have this really nice async thing going where you have a task-based UI. It triggers the command to the backend, and the event stream is actually eventually going to update the stream. So that's something we didn't talk about. It's perfectly possible. Another thing that we haven't talked about is HOCON configuration. HOCON stands for Human Optimized Configuration Object Notation. It's something they got from the JVM ACA. It looks like JSON. It's not JSON. It's a pain in the ass, but it is the way to configure actor systems. For a lot of reasons. For instance, configuring these router pools or these routing groups. That's something that you might want to do in configuration and not in code, so you can actually have that whole config in a Hocon config file and load that in when you start your actor system. Clustering, I've mentioned it a few times, haven't shown you how to do it. I would need like a whole other hour just to go into all the intricate delicacies of clustering with Akka.NET. Then, of course, logging. There are adapters for everything. If you're not running on containers, because then you want to log everything to standard out, you can basically use whatever logging system you're used to using. And one of the very important things when you run Akka.NET in production is you can basically buy, and that is the only paid product that Petabridge, the company that maintains Akka.NET, puts out, that is Phobos. It allows you to monitor inbox sizes, actor counts, dead letter stuff. I mean, the newest version or the next version will plug into OpenTelemetry, so there's that. The license is, I think, 4,000 euros a year, and it allows you to basically, with confidence, run a distributed actor system in production. So if you're going to do this at any kind of scale, definitely look into that. So if you're triggered after today and you want to learn about Akka.NET, there is a beautiful free boot camp on GitHub. So that takes you through all the basic features and stuff that Akka.NET can do. The Petabridge blog is a gold mine. The people from Petabridge, when they develop new features into Akka.NET, they always blog about it. They explain how it works and how it works behind the scenes and everything. So if you're willing to look there, you're gonna find pretty much all the information that you need. If you want to train your team, they offer remote paid training. They have 3 courses that they actively promote, which is design patterns. I highly recommend, if you're doing anything with a whole team in production, at least take that one. Because the patterns that you use when you're doing actors, they're different from the patterns that you're going to want to use when you do an object-oriented system. And it's all covered in a couple of hours, and you're going to get taught by one of the people who are actually building it. So if you have questions, you're going to get the people who made it, which is fantastic. There's also a course on remoting and clustering. Didn't really touch on those. But just remember, DDD and actors, they are a match made in heaven. You can make a very, very expressive software system with very expressive tests if you do this. My name is Hannes. I'm the head of learning and development at a company called Access in Belgium. This is my Twitter handle and my ICQ number. Make ICQ great again. If you have any questions, we have 1 minute. But it's lunchtime, so I don't mind sticking around for 5 minutes if you have questions. You're all hungry, I get it. Okay? It was so hacked together during the last week. I'm probably going to publish the repository soon, but I need to clean it up. Because I made all of the actors and all of the tests, but yeah, I'm going to be open about it, right? But no, hit me up on Twitter and I'll ping you when it's up, because it should be on GitHub one of the next few weeks. Other questions? Okay, enjoy your lunch. Don't forget to vote.